We're continuing with section 17.2 Stokes theorem, and we want to discuss vector potentials and surface independence. So before explaining what surface independence means, we have to explain vector potentials. A vector potential for a vector field F is a vector field A such that F is equal to curl of A. So if F has a vector potential, then its integral over a surface S depends only on the boundary of S because of the Stokes theorem, and this is how it goes. So the vector potential of the integral over S of F is going to be equal to integral over S of the curl of A, and that is, in this one, according to the Stokes theorem, is going to be equal to the line integral, the contour line integral of A dr. And so, knowing this, basically, if F is a curl of another vector field, only the surface integral only depends on the boundary. We wonder if we can swap a surface by another and compute the surface integral in an easier way. And so here's an example. Look at the surface S1 and surface S2. Both of them only have this boundary. Both of them have the boundary in common. And so if there is an F that is a curl of a vector field A, then basically the surface integral of that F over the green surface or the blue surface is supposed to be the same thing, and it's going to be equal to this integral over the boundary. Now, how does this make our lives easier a little bit? We basically swap a surface for another easier to compute surface. And so if S1 and S2 have the same boundaries, including the orientation, and then the surface integral of curl of F over S1 is equal to surface integral of curl of F over S2. Now consider the surface S in R3, that is x squared plus y squared equal to 2 plus z minus e to the power 2z, for z bigger than equal to 0, oriented by right hand rule, and that is again, when you walk across, you have to get it going this way. Now, if the surface is oriented outward, the normal. Now, let f of x and y and z be x squared y, negative x y squared, and x y z. Evaluate the surface integral of the curl of f ds. So first thing, I know that I have to compute the curl of f. So let's find curl of f. Curl of f is going to be equal to ijk partial x partial respect to y and z of x squared y minus x y squared x y z, and then that would make it this two partials, partial of x y z respect to y, which is y z, minus partial of negative x y z, negative x y squared respect to z, which is 0. So yz times I, then partial of xyz with respect to x, which is yz, and then partial of x squared yz with respect to z, which is 0, and then partial of negative x squared, negative xy squared with respect to x, which is negative y squared, minus partial of x squared y with respect to y, which is negative x squared. Okay, so I found the curl, which is this. Now, thinking about that curl and any of these surfaces, computing parameterizing the surface that is given is going to take a long time, and computing all the related material takes a long time. Is there any better surface to use? And yes, there is. If you look at the basically the intersection of the current surface with xy plane, you will end up with a circle. That circle x squared plus y squared equal to 2 plus 0 plus minus 1, that is 1. So there's a circle x squared plus y squared equal to 1, and so you can imagine a disk of x squared plus y squared. Down in here it would be x squared plus y squared less than equal to 1 and z equal to 0. So use that disk to basically instead compute the surface integral. And so what is that disk? The disk is r cosine theta and r sine theta, and z is equal to 0. So now, so this is g of r and theta. Now g of r is going to be cosine theta, and y with respect to r is going to be sine theta and 0, and then g sub theta, or the partial respect to theta, is going to be negative r sine theta and r cosine theta and 0. Dot product of the two is going to give you g r cross g theta will give you r cosine squared plus r sine squared. So that's it gives you, that's a cross product 0 0 and r. Now parameterize this surface also, and that would give you y and z 0 and 0, and here it gives you negative r squared. So dot product of those 0 0 and negative r squared dot 0 0 and r ends up to be negative r to the third, and we're integrating over the disk, so 0 to 1 and 0 to 2 pi negative r to the third dr d theta. Again, here, when you were evaluating, because we basically found the normal vector and we parameterized everything, the Jacobian was included already, right? It's using the formula, you are only using the parameters here, but the Jacobian over there is already included because of all the computation. And so basically this is going to be negative r to the 4th divided by 4, 0 to 1, n equals 0 to 2 pi d theta. And that is 1/4 of theta 0 to 2 pi and negative 1/4, and that is negative pi half. So we ended up, instead of computing the surface integral over the blue surface, we computed into the over the disk, and the values are going to be the same for both of the basically surfaces. And so now it's the question of the rubber ducky, and I click on question 17.2c. Let S be the surface of a rubber duck shown to the right, and let F be a vector field. What is the value of surface integral of curl of F ds? And so give yourself a quick minute. And so what happens is that if you draw a boundary or a belt for the rubber ducky, and the belt is going to divide rubber ducky into two surfaces. One surface, the tails and all, and one surface, heads and all. So two surfaces. But then the boundary, whichever direction you get, is going to be, if you want to make the boundary the right hand side for the tail part, is going to be the opposite of the boundary with the right hand rule for the head. So the right hand rule for the tail and right hand rule for the head is going to give you different direction of the boundary. And so when you add up with the same direction boundaries, which is the rubber ducky, the belt only has one direction. If you add the two surfaces together and take the surface integral, instead of both pieces being equal to each other, one is the negative of the other, so they add up to 0.